Okay, let's go through these extension questions. Obviously, the answers are at the bottom of each question in your book. So if you got them right, you don't need to worry about going through the solutions. But if you want to see how anything's done, here they all are. Force diagram for a 900 kg car that exerts 5,000 newtons of traction force being opposed by 1,000 newtons of friction and drag forces combined. So my car meant to be on a level road, and downwards and upwards should be the same size. My normal force, my gravity force. Traction helps it move forward, and there's 5,000 newtons forward. And there's only 1,000 newtons back. Friction. Right, a net force equation for the car. The upwards and downwards of forces to balance. So net force only has to worry about forward and backwards. So the net force is equal to traction minus friction. Calculate the acceleration of the car. So I want to calculate the net force first, and that is 5,000 minus 1,000 equals 4,000. And then from that I can say, well, net force equals MA. If I want to rearrange this to find A, I have A equals net force over M. In this case is 4,000 newtons over 900 kgs, and that is 4.44 meters per second squared. Okay, these ones get a little bit difficult, but not the end of the world. 3 modified at-work machines have blocks of mass EM on frictionless table hanging ensuring the blocks release the accelerate as they did in our lab. Which system has the greatest net force? So if you think of the whole system, when you think of the whole system like this, you can actually, the pulley just transfers force from one direction to another. So instead of that, you can actually draw the whole thing, knowing that there's a force here, there's a force here, there's a force here, there's a force pulling up, and there's a force pulling down. Those two are the same because it's not going up and down through the thing. You can actually pull this around and redraw it like this. Here's my pulley. Alright, you've still got this one up, you've still got this one there, but now you've rotated this around, so that force that's across is now going down, and these two forces that are cancelling out are like this. And so what you see is they cancel out. This is a tension force, it's the same string, this is the tension force, they are the same as each other as well. So they, within this whole system, they cancel out. So you're left with the only thing providing the net force is the force of gravity on the hanging blocks. It's the only thing that isn't being cancelled out by anything. So then for this question, which system has the greatest net force? It's really which system has the greatest force of gravity on the hanging blocks, and that's obviously system C. Which system has the least inertia? Inertia is like mass. So the least inertia, and obviously that's system A because it only has 2m. All the rest have 3m. Page 7, on the next page, determine the acceleration for each system. So I'll do one of them and then you can go through and do the rest. I'm going to do system B because it's just, it looks harder than system A. So the net force providing, remember how we said was what's hanging? So in this case it's mass times gravity is hanging. And we also know that net force equals MA, so mass times gravity equals the mass in the system times acceleration. Now the mass in the system of B, because we're looking at B, and B is 3 masses. So the mass in the system is 3m times A. I'm going to rearrange by dividing by 3m, dividing by 3m. and I get G over 3 equals A. And that is what I got there. Okay, so just really quickly again, the net force is given by, in this case, is given by what's hanging, and I go through the reason for that when I did part A of the question and the slide behind. Right, when I redrew this like that, and so that was, in this case, there's only one hanging, so that's why it's mg. If there was two hanging, like in system C, my total force is going to be equal to 2mg. And then I go through the same process. And I know my net force is equal to ma. This m here is the mass of the whole system, and if you've got 3 blocks, that's why it became 3m. Cool, and last question. Child takes a trip down a slide, draw a quantitative force diagram for the 30 kg trial. Quantitative means with numbers. So we've got the force of gravity is going to be 30 times 9.8. But where is my calculator? I might just pause this and go. Okay, I found it. Right, back to here. Go away. Okay, 30 times 9.8, 294 newtons. We've got some normal force up here. Don't know what that is, and we've got some friction force here. That's 160. Okay, find the net force on the child. Here's what I'm going to do. When I've got these sort of triangle ones, the issue is it going down at a constant speed because of the friction, or is this not enough friction to make it go down at a constant speed? I'm going to deal with the situation as though there's only these two forces, gravity and normal, because I can do that. I've done that before. When I put them together in a force vector addition diagram, force gravity, force normal, that's my net force. I'm going to pretend there's no friction. I'm going to work out what this is now. I know this is 55 degrees. So this is the right angle, this is the hypotenuse, this is the adjacent, and this is the opposite. So if I'm working with net and gravity, I'm going to go sine 55 equals opposite F net over, and gravity we know is 294. When I rearrange that, I get F net equals 294 times sine 55 equals 240. 0.8 newtons. So that's what the net force is if there was no friction force. However, there's 160 pulling backwards. So my actual net force is actually 80.8. Okay, I'm going to get my working up here. So I want to, I found the net force. That's what I want to do. Net force on the child, 80.8. Cool. And then the child's acceleration is just net force equals ma, a equals force over m, 80.8 divided by 30 kgs. .669. which equals 2.7 meters per second squared to two significant figures. Yeah, it's a tough question. It is. And let me draw it again. The child's going down the slope like this. We definitely know there's gravity, normal, and friction. The issue is when you put them together, and you do a vector addition diagram, in this case, the gravity, the normal, and the friction. The friction doesn't get all the way back here to the starting point. And so the net force is whatever's left over here. Okay, so that's the net force in there. That's why that's really hard to deal with. So that's why I pretended this didn't exist, and I just wanted to find the whole length of this side of the triangle. Once I found that, that's what I did in this process here. See, I'm finding the whole length of it here, pretending friction doesn't exist. And then when I had that, which was 240, then I minus the 160 to find out what this little tiny bit in here was. So it is a tough process, but that's why it's in the extension questions. Okay? Let me know if you've got any questions, just give me a bell.